This is problem number 24 from the spring 2018 exam. This is also for a student who requested that I do any loop-de-loop problem, so here's a loop-de-loop problem. We have a mass that starts at a height h. At that height, it ends up going around and it reaches the top of a loop-de-loop with a normal force of 40 newtons pushing against it. We are asked what height is h. So let's talk about the situation here. The mass starts out with some amount of potential energy. That potential energy gets converted to maximum kinetic energy here. Then it comes around the top to this point where some of the energy is now potential energy again, but it has some kinetic energy left over to clear the loop. We know in terms of forces that since this is uniform circular motion, the force pushing on the mass at the top has to be equal to mv squared over r to keep it going in a circular motion. And so the first part of this problem is to think in terms of the forces at the top of the loop-de-loop. Here's our free body diagram. At the top of the loop-de-loop, the mass is experiencing two forces. It's experiencing its own weight, but it's also experiencing that extra normal force pushing down on it. As you guys will remember, with a loop-de-loop, there's a minimum amount of force needed to keep it in or there's a minimum speed necessary for it to clear this loop-de-loop. And at that minimum speed, all of the force necessary to keep it in a circle at the top is provided by the weight. If it goes at a faster speed, the weight is not enough to keep it going in a circular path, and the track's normal force itself holds it in the circular path. So we know that this mass was going at a faster speed than the minimum speed needed to go around the loop-de-loop because it is experiencing a normal force in addition to its weight. If we write this out, we know that the normal force plus the weight equals the centripetal force, the force keeping it in a circular path. We also know that the equation for centripetal force is mv squared over r, so we have that n plus w equals mv squared over r. What we don't know is the velocity, but we can now solve for it because we know the normal force, the weight, and then mv squared over r. When we solve for those numbers, we get approximately 80 equals 20v squared, and we get that the velocity is 2 meters per second squared. Now, in order to figure out at what height it would have to have started at, we rely on conservation of energy, and we know that the initial potential plus the initial kinetic energy has to equal the final potential plus the final kinetic energy. The initial potential energy is mgh, and the initial kinetic energy is 0. The final potential energy at the top of this circle is mg times the height, which is twice the radius, plus 1/2 mv squared, where v is what we solved for. It's the velocity at the top of the circle. And now we just plug in the numbers. The m's cancel out. We can plug in g, so we get gh, 9.8h, equals 9.8 times 0.4, that's twice the radius, plus 1/2 v squared, which is 2 squared, which is 4. And when we solve for the height, we get 0.6 meters, and that is the solution.